All right, so in this lecture, I want to cover Newton's universal law of gravitation, which is this right here. It says that Fg is equal to G m1 m2 over r squared. This showed up in the video on Newton, if we got a chance to watch that in class. What it says is that planets aren't special in their ability to generate a gravitational force, meaning that any object can generate a gravitational force. So a marker sitting on a desk creates a gravitational field around it. I am creating a gravitational field around me. The school is creating a gravitational field around it. The desk has its own gravitational field. So the question becomes, well, how do you, if all these objects generate a gravitational force like the Earth does, then why don't we notice it, right? And the idea being that we notice planets like the Earth so much because they're so massive, and things like a desk, we don't notice it pulling on us because it's just so small compared to the mass of the Earth, right? So objects generate a gravitational field if they have mass, but it's only large enough to notice if the mass is large enough. So here you can see with this, you can think of this as, sometimes I like to call it Newton's fourth law. It's not really Newton's fourth law, so don't go around, saying that, but you can think that it is, and because that's how important it is, right? Let's talk about some of these variables here. G is the universal gravitational constant. So I think I got some room over here to write this down. And it's just a number, but it's a very small number. But it's useful in in a calculation of any force for any object or any two objects, and that we have this constant in there, G. Now it is 6.67 times 10 to the negative 11th, the negative sign indicating that's a very small number. We don't know, or I know the units for it, but I'm not going to worry about it. So we don't really worry about the units. Just realize that when you use this formula and you plug in masses that are in kilograms and an R that's in meters, that you're going to get newtons out at the end. So we could figure out the units for G, but it's really not that important right now. And I'm a pretty big stickler for units too. So if I'm saying it's not that important, just don't worry about it right now. And if you ultimately, after you use this formula enough, you want to come back and learn the units, you can, but it's nothing groundbreaking or anything. So, okay, what else can we say? M1 is the mass of object 1. I can probably just write these right here. And this has to be in kilograms. Just go ahead and write kg. This is the mass of object 2. And this is also in kilograms. So what we're seeing is that there's a force of gravity between any two objects. And this formula is going to quantify that, right? Okay, R is, or give us a number for it. R is the distance center to center. Now it is not the radius. And that's important to understand. It's in meters as well. And it's important to understand that that's the case, because a lot of times students see that R and they want to think radius. So we have, whoops, let me undo that. I was trying to get the highlighter, just trying to make this a little clearer. So we have the mass of object 1, the mass of object 2 in kilograms, distance center to center in meters, and this is going to get squared, right? We should notice that this is R squared. And that's very important because you don't want to forget to do that. You get the answer wrong. All right, so that's kind of what we have here for the force of gravity. If we calculate this, then obviously we're going to get units of newtons. Let me add a page here. I just want to write a little bit more here. So I'm going to add a page above this. And then, let's see. Somehow, okay. So let's go back to this. So what I want to say is that this formula for Fg, this new one we just learned, is the same as this one, right? It's just written a little differently. And obviously one is much more universal than the other, because this one's, the bottom one is for any two objects, and the top one, we've always assumed that this is 9.81, right? But that goes with the fact of assuming that we're always on Earth. What if we don't assume that, right? What if we write that a little more universal? Then what I'm trying to say is, what if this is just the gravitational field of any planet? And so my point is that we can think of this as being kind of a form of the equation underneath. So what I'm saying is we can think of the formula we've used up into this point, right? Fg is mg, is kind of a form of the universal gravitational formula. All I'm going to do is just write it a little differently. We'll say that the mass of object 1 is the mass of maybe u or something. And because really this is a formula for weight, right? Maybe you want to calculate your weight in newtons. That'd be the mass of u then, and you're on the planet Earth. You multiply by 9.81, you get newtons, assuming your mass was in kilograms. And so what I'm saying is that this gravitational field is equal to g times the mass of object 2, which would be the Earth, over the distance from the center of u to the center of Earth, which is really just the radius of Earth, right? And we'll just go ahead and square that. So what I'm saying is this number, or this quantity right here, is 9.81. So that's where that number comes from. Okay, so just kind of peeling away this formula a little bit to see why 9.81 is the number we use, right? But if it's any planet, then obviously that this is if I wrote this more universal, then the number wouldn't have to be 9.81. What am I trying to say? Well, we could just make this, get rid of this 9.81 for a second, and say that this is just the mass of any planet, and this is the radius of any planet. And you can see we have a generic formula then for finding the g of a planet, whether that's the moon or that's Jupiter or whatever. All right. Anyways, enough about that. Let's go ahead and look down here at this formula and how we use it. All right. Let's give it a shot here, and I think it should be fine. Okay, number 1 says, what is the force of gravity between a 100 kilogram person and a 5 gram pencil that are 0.25 meters apart? So with these problems, you always want to start by writing the formula out. This helps you remember it, and it's just a good skill, a good way to do problems, right? Because you're learning the formulas. All right, so I'm going to go ahead. We want to know, what is this force gravity? I think that's what they ask us, right? Yeah. And we're going to just go ahead and put the numbers in. 6.67 times 10 to the negative 11th for g. The mass of the person is 100 kilograms. Notice we're not asking about the force of gravity with the earth, right? It's just between this person and this 5-gram pencil that's on their desk or something. All right, so the 5-gram pencil, 5 grams. So we should be able to move our decimal here. We're going to have to, let's see, grams is here. We have deca, hecta, kila. So we'll have to move it. Let's see here. Start at grams. 1, 2, whoops. Okay, 1, 2, 3. So 3 to the left to get to kilograms. So we're saying 1, 2, 3.005 kilograms. And then divide by the distance from center to center with the two objects. So this is the 0.25. We'll go ahead and square that, and that's in meters. So now it becomes a calculator problem, and this is where students struggle sometimes because they don't know how to use their calculator right. And I'll try and go over some of this in class and how to use it correctly. But let's go ahead and just solve here. What I like to do that helps me, and I was kind of running out of room. This is kind of crummy for this sheet. So let me just go ahead and spill over into the space down here. I like to crunch the top and then crunch the bottom separately. So if we do that and plug that in our calculator, we get 3.335 times 10 to the negative 11th on top. Units are, we're not going to worry about units right now. It would be kg squared, but we know that the big G has different units, so I'm not going to worry a ton about that. And on bottom, I would have units of meters squared, but once again, not going to write it, 0.0625. Okay, so we'll just plug that in our calculator one more time and get 5.336 times 10 to the negative 10th newtons. Oops. Okay. So there it is. This is a very small force, not even close to being a Newton, right? And it takes 4.44 newtons to equal a pound of force. So this is much, much, much smaller than a pound of force, right? This is like more like 10 billionths or 53 billionths of a Newton, not even close. So to 1 whole Newton. And yeah, so this is why you wouldn't notice a force of gravity, say, between you and a pencil sitting on your desk. All right. So that's good. I think we're kind of getting that. But you know, we'll practice more of those in class. I just wanted to go over it. Let's move on to a more conceptual understanding of the universal law of gravitation. So you can see right here I wrote it, and what we're going to do in these kind of problems is we're going to set. Let me say one more thing too before I move on to this, because I know I forgot to say this and I thought it'd be neat to include that if you were to graph, say, the force of gravity in newtons versus r, right? You would get a relationship, an inverse relationship, right? Which actually inverse squared. The force gravity is in an inverse squared relationship to r. So what I'm trying to say is that Fg is proportional to 1 over r squared. And if you graph it, it looks a little like the inverse relationship graph. So it ends up looking a little bit like this. And I just wanted to point that out because it's not a bad thing to start to notice that. And this is if you made this graph of Fg versus r. Okay, so, all right, let's go ahead and move on here. On the next part here, universal law of gravitation conceptually. So what we're going to do is we're going to say that anytime we see this right here, that is going to equal the variable f. And so we're going to manipulate something about this relationship between these variables and change our force gravity to be something new. And we want to know what it is in terms of f. All right, so what is F then? F is the force gravity between the two objects. Let me go ahead and draw two objects up here and show you really quick. We'll say that object 1 is right here, is this circle right here. Object 2 is right here. We'll call this M2. And the distance from center to center is R. And we know that there's some force gravity between these two masses. And we know that force gravity is equal to, once again, Fg is equal to G M1 M2 over R squared. And this we're calling F. So this force right here is F. Now, what happens, though, to F, or to Fg, right, the force gravity, how does it change compared to the original force when we make changes to these objects? So, for instance, in the first problem, it says if the mass of one object is tripled, what is the new force? So if I come up here and I triple one of these objects, if I show a picture for it, maybe I triple mass 1. So this is M1, but it's tripled, right? So I'll call it 3 M1, 3 times M1. All right, and then I have mass 2, mass 2 just sitting here. Distance center to center is still R. And so we want to know how that affects the force, right? So before, Fg was equal to F. But now we can say that we have a new Fg, right? So I'll write it right up above. I have room. Fg new. And it's equal to G, whoops, dang, that wasn't even close, is equal to G 3. I'm going to write the 3 in red. Actually, yeah, I'm going to write everything that's different in red. 3m1 times m2 over r squared, right? This is my 3m1. And what we can see is if we pull this 3 out front, we see that Fg new, which is what we want to know, is equal to 3 times G M1 M2 over R squared. And so the reason I'm doing this is because I want to show you that this new force gravity is equal to 3. And we said that whenever we see this quantity right here, that we said that is going to be the same as F. So we can now write this new force gravity in terms of F. So I'm going to go ahead and write this. Dang, I lost it. All right, right here. Okay. Getting distracted there. All right, so, okay, so there we go. There is our answer. That the new force gravity, when you triple one of the masses, is equal to 3F. So if you keep things normal, right, it's equal to F, just like this. But as soon as you triple one of the masses, the new force is 3F. That's what I'm saying. Okay, so this is conceptual, right? It gets at the idea of the universal law of gravitation without really having to do any math, but more just think about what happens, right? It's an interesting question. What would happen if Earth was 3 times as large and we kept the sun the same size? How would that affect the force of gravity between the sun and the Earth, right? So it's an interesting question. So I'm going to go ahead and write the answer down here for problem 1. I'm going to write 3F, okay? Okay, then it says the next one. I'm actually going to skip number 2. Let's go to, let's go to number 4. I'm trying to think if I want to do number 3, though. No, I think I'm going to leave that for you guys. All right, number 4, the distance between the objects is doubled. Okay, so the distance between the objects, we have to remember that this is r, right? And so we are going to double r. And this is where it starts to get a little trickier, because whenever you mess with r, it's a tougher problem. Let me add a page here. Okay, so it's a tougher problem because of the squaring. So I'm going to start here by, I'll just write the formula out. I just like to have it here because I'm going to, write a number in there. Okay, so there's the formula, right? And that's equal to F, obviously. But this is all going to be about FG nu. And so we are going to double R. I think that was what it was. So I'll put a 2 right next to the R. Now, it's not that simple, right, because of the squaring. So what I got to see is that the 2 is inside of the squaring. So therefore, when I double R, I end up squaring the 2 as well as the R. Okay, so let's rewrite it then. So what we're saying is FG nu is equal to G M1 M2 over, R squared is just R squared, but squaring the 2, we get a 4 down there hanging out on bottom. So I'm going to go ahead and push the red number out in front and rewrite. So I have FG nu equals G M1 M2. Oh, dang, I forgot to write that red number out front. Let me rewrite that one more time. So I'll start by writing the red number. Now I'm going to put a 1 on top, right? I can do that because it's on the 4 is on the bottom, so there has to be something on top there. So anyways, I'll write what's left. And we know that this, right, is F. So we can see that FG nu is 0.25 F, a quarter F, 1/4 F, something like that. So this is what happens if you double the distance. So if you were to take a planet and move it twice as far from the sun, then the force of gravity would be 4 times as weak. So this is what we mean by the inverse square law, right? When we say Fg is proportional to 1 over r squared, meaning if you double the distance, you don't have the force, right? It doesn't get half as weak. That would be an inverse relationship. When you double the distance, right? So I'm saying if you were to double the distance, it's not half the force over here, right? That's not the idea. It's actually a quarter of the force because the 2 gets squared. That's why. And so it ends up being 1/4 the force when you double the distance. Okay. Let me erase that. Let's get that out of there. Okay. So we'll come down here and write the answer here. So we have 1/4. Whoops, I wrote it in the wrong blank. I think we were on problem number 4. So that'll be 1/4 F, or a quarter F. Okay, good. Let's look at number 5 here. The distance between the objects is tripled. Am I going to do this one or not? Just thinking about this. Yeah, I guess we'll go ahead and do this one. All right, so we're going to triple the distance instead this time. So I'm going to try and keep this right here, right? Because this isn't all that different. So instead of a 2 here, let me just erase what's in red here. Just go through and instead of a 2 here, I have a 3 here, right? And so we end up squaring the 3. What's 3 times 3? That's 3 squared is 9. The r gets squared. The 9 comes out in front, but it's on bottom, so it's 1/9, and we end up with 1/9 F is what we're saying here. So hopefully you can see all that, and it's not cut off by the screen at all. So anyways, down here, I'm going to go ahead and write 1/9 F. Okay. And I'll let you do the next one, number 6. Let's go to number 7. 7 says the distance between the objects is halved. Now, if we doubled the distance, we ended up with 1/4 of the force. So if we have the distance, we should get how much force? Well, 4 times the force. All right, let's see if that makes sense. So we're saying, once again, if we half R, we get 4 times the force. How is that going to work mathematically? All right, so let's get another page here, or can we just do it? I think I can just do what I just did a second ago. Let me just do the erase technique. It seems to be working for me. Hopefully it's working for you. Okay, so, and it saves me a little time from writing that. All right, so we're going to half the distance. So the force has to get stronger, right? If you take 2 objects and put them closer together, then the force should get stronger, right? We're making R smaller. This is the inverse squared relationship, right? When R increases, FG gets larger. That's the inverse part. When R doubles, we said that force of gravity gets not just weaker, but 4 times weaker. So that's the squaring part. So now we're going to make R smaller. So the inverse of getting smaller would be getting larger. So force of gravity's got to get larger. And we're saying if we have R, that it should get 4 times larger. Let's look at that. So coming back to here, I got this half. I got a fraction in my fraction. It's the worst. So we're going to square the 1/2. So let's do that. Let's make that 1/4. Does that make sense? It should, right? Multiplying fractions is easy. 1/2 times 1/2 is equal to 1 times 1, 2 times 2. It's when you add them that you got to worry about common denominators and all that. So we're just saying 1/4 hanging out on the bottom. But we have a fraction in our fraction. I think we got to do that like keep, change, flip or something. I don't know how that goes. But I know you multiply by the reciprocal. The reciprocal of 1/4 is 4/1, so we're going to multiply by that. And so the 1/4 on the bottom becomes a 4/1 out front, which means 4/1 times F, or just 4F. And so there's our answer. When we have the distance, the force has to get stronger, but it doesn't get twice as strong. It gets 4 times as strong because of the squaring effect. All right, so we're going to say that was for number 7. All right. And should we do one more? Oh, boy. Let's do this one on the bottom. Let's give this a try. Let's try number 11. And... maybe I should save these for you guys. Yeah, I think part of the fun is trying these on your own. You got the basic skills now, so give some of these a shot on your own, and we'll talk about them in class. We have some more practice here, which we're not going to do right now, and then some more practice here. Something to note here is that they take the universal law of gravitation and rearrange it and write it for the distance. You don't always want to solve for the force of gravity. Maybe you want to know the distance center to center between 2 objects. And so you can solve for other variables in this equation. And yeah, I thought that's kind of neat. So this is in practice C here. Anyways, we'll work on this in class, and that's pretty much the lecture there. So have a good day.